This video will walk you through how to use an exploratory data analysis tool built using Trelliscope to allow for interactive visualization and interpretation of nanopot proteomic imaging of a mouse uterine cross-section composed of multiple cell types. Trelliscope is an open-source R package that combines analytics and visualization so that users can explore their data in a dynamic fashion. For more information about Trelliscope, visit deltarow.org. When you open the Trelliscope viewer, you're presented with options for viewing different displays. In this case, our options are for 3 different types of datasets. One is based on the stroma image, another on the luminal epithelial image, and a third on the dominant cell type dataset. These 3 datasets are available at the protein level as well as at the peptide level. They are also available using MaxQuant as well as using MaxQuant match between runs. We will select the MaxQuant stroma image dataset. This takes us to a heat map for a single protein, 1433B mouse, where the heat map cells are colored according to the log2 normalized expression level, and the numbers in each voxel cell are colored according to the dominant cell type in that voxel. This is one protein out of 2,298, and we can click on the arrows to scroll through subsequent proteins. We have the option to look at more than one protein at a time using the panel layout. We will look at a 2x2 grid to see 4 proteins at a time. Now we have a total of 575 displays, where each display contains 4 proteins. We can change the display back to one protein at a time by returning to the panel layout. Another useful display option can be found by going to Related Displays, where we can select the optical image and have it display side by side with the heat map. Again, we can click on the arrows to scroll through different proteins. To remove this related display, return to Related Displays and uncheck that optical image. For each protein, we've stored multiple characteristics. A subset of those are automatically populated below each image, and you can find the full list of available characteristics under Panel Labels. Here we note that the characteristics with checkboxes are the ones that are already being displayed underneath each heat map, and we can add or remove characteristics that we would like to see displayed. We have things like the primary gene that a protein is associated with, the enzyme commission number, as well as statistical values that have been calculated. We can use these characteristics to sort and filter the proteins down to a subset that might interest us the most. We do this using the Table Sort Filter feature. Here, each characteristic is listed in a column. If we're interested in searching for secreted proteins, for instance, we can scroll until we get to cell component keywords and type in secreted, and then click Apply. This filters the dataset down to the 136 proteins that all have secreted proteins listed as a cell component keyword. As we noted before, we can click through these proteins one by one. And here we notice that in some of them there seems to be a clear gradient going from the top right to the bottom left in terms of expression level. If I find a particular protein of interest and want to learn more about it, I can click on the link down here that will take me to the UniProt page for that protein. If we're interested in what the data for this particular protein looks like in the dominant cell type dataset, we can click on this link and it will take us to the box plots for this particular protein in that dataset, where we can see that the stroma cells have higher expression values than the other 2 cell types. Note that at the bottom of the screen, the state tells us what has been applied to the data. In this case, we have one filter applied. We can also apply other filters on top of this or reorder the proteins according to a different characteristic. For instance, we may want to sort these 136 proteins based on the number of peptides used to quantify to it. nanoPOTS quantify lists the number of peptides used to quantify to each protein, and we can click on these arrows once to order from smallest to largest, and twice to order from largest to smallest. Now we can apply that sorting and view our 136 proteins in that particular order. To remove an ordering or filtering, we can go down to the bottom of the screen and click the X next to the box. So clicking this X will remove the sorting by the number of peptides used to quantify to the proteins, and Xing out of this box will remove that filter. So we'll go from the 136 proteins back to 2,298. Another way to filter the proteins is to use the univariate filter. Here we can select one variable to use to filter the data. For instance, we could filter using the log2 fold change between the luminal and the stromal cells. What appears first is a quantile plot that shows the quantiles for the log2 fold change of every protein in that data set. If I'm interested in the proteins with the highest log2 fold change, I can click and highlight the ones that I'm interested in. Alternatively, we can view a histogram and make our selections using that plot. If we apply this filter, that takes us to the 34 proteins that have the highest log2 fold change between the luminal epithelial cells and the stromal cells. To remove this filter, we can again go down to the state bar and click on the X. A third way to filter your data is to use the bivariate filter. Here we get to select two different variables to use to filter the data. We will again select the log2 fold change between the luminal and the stroma cells. And we will also choose the number of tissues with non-missing abundance values. This graph shows a grid with every combination of these two variables and hexagons whose size indicate the number of proteins that fall into that combination. On the right of the graph are the proteins that were seen in the most voxel cells, and in the top of the graph are the proteins that have the highest log2 fold changes between the luminal and the stromal cells. If we select proteins in the top right of the graph, we can apply this filter and get down to the 37 proteins that were the most highly confident and largely differentially abundant between the luminal and stromal cells. From here, if we're interested in investigating proteins out of these 37 that have secreted as one of their cell component keywords, we can add an additional layer to the filter. We go to the table sort filter and scroll to the cell component keywords. To reiterate, we've reduced our data set down to 2 proteins using filters. We started by looking at a bivariate filter where we restricted to the proteins that had the highest log2 fold change between the luminal and the stromal cells, that were also observed in nearly all voxels, and that contained secreted as one of their cell component keywords. If we're interested in viewing the peptides that map to this particular protein, we can click the peptide link at the bottom of the screen. This brings up a 4x4 grid showing the peptides that map to that protein. We can see at the top of the screen that there are 6 such panels, so there are up to 24 peptides mapping to this protein. If we enter here the 6th page, it'll take us to that last set of panels, and we see that there are 3, so there are a total of 23 peptides mapping to that protein. Going back to that protein display, another option that we have is to look at the data from the max quant match between runs for this protein, and clicking this link will take us there. Here we've demonstrated a subset of the capabilities of this tool for interactively exploring the data. To switch between data sets, click on the folder in the upper right-hand corner of the screen and select a different data set to explore. Now we're viewing the data from the luminal epithelium image, and we can start exploring from here.